Today we're going to take a look at some set operations. So we've talked a little bit in section 2.2 about some sets. We've drawn some Venn diagram pictures. Is that true? Have I drawn Venn diagram pictures? Some of my classes are bleeding together in content right now, so I'm asking. Okay, good. And we're going to look at some ways that we can compare or combine sets together in this section. So our first set operation we're going to look at is called set intersection. Set intersection is the set of all elements common to both sets. So what you want to imagine is what we mean by the word intersection of streets. So if I talk about the intersection of Kickapoo and MacArthur, it's exactly where they cross over on top of each other, right? It's that crossing section in the middle. It's what they have or share, have in common or what they share. The set notation for that looks like this. Okay, so it's an upside down U. It's an intersection. And this is the set of all x such that x is an element of A, and, right, that's that keyword and, x is an element of B. That's what makes it in common to both sets. And the Venn diagram picture, you don't have to draw it as big as mine. I just have more space on mine than you do. Looks something like this. So we have two sets, and they overlap a little bit. And specifically, the intersection is the overlap. Okay? So that's an intersection. The next one is called a set union. So this is the set of all objects in one set or the other or both. So the notation actually looks like a U. And the set description is very similar. It's the set of all x such that x is an element of A. Or, okay, that's the key difference. The word or is here. X is an element of B. So what you should notice is that I didn't write down or both. Okay, so in mathematics, unless specified otherwise, or means either or both. It's called an inclusive or. It includes all possibilities instead of excluding the possibility of both being true. So when you think of, I told you up here to think of street intersections, right? When you think, that's terrible streets, but pretend like it looks better. When you think of a union, what I want you to think of, I want you to think of marriage. So what marriage does, and what the preacher says at the altar in most traditional, ceremonies anyway, is, the two will become one. That's the phrase that you hear, right? The two will become one. What does it mean? Well, it means that all of my debt becomes my husband's debt, and all of my husband's assets become my assets, and all of my children become his children, and whatever it is that we each individually bring in, it's now all ours. It's a joint pot of stuff. There is no yours and mine anymore from that standpoint. That's what we want to think of when we think of union. And so when we think of drawing a Venn diagram for it, we have those same overlapping circles we had before. And we label them the same way. Here's A, here's B, here's the union, the universal set. And we get all of A and all of B all in one big happy family. Right? One big pot of stuff. That's a union. And the third one that we're going to look at is called, relative difference. So this is the set of all elements in one set that are not in the other. So we're going to look at this one, A minus B. So difference looks very much like subtraction when we talk about a difference in elementary school. And this one would be the set of all elements in A. So x is in A. And x is not in B. And while you may have varying levels exposure to or descriptions of, a prenup is actually a pretty good description of this. Okay, so what really happens in a marriage is that, I bring in all my stuff, the person I'm marrying brings in all of their stuff, and there isn't any overlap at the beginning. I mean, like that's what it should look like, right? There really isn't any overlap. We haven't joined our accounts. We haven't this, we haven't that. And now when we're joining together, there's all my stuff, there's all your stuff, and then we're pushing it together. And then from this point forward, moving forward, there's some things that become our stuff. Maybe we jointly go and we buy a house. Now that's in that sort of overlapping category. So when we're thinking about a prenup would say that the things that I brought in are the things I take out. That's generally the idea of a prenup. And they're often done when one person has far more wealth than the other person. That's a general idea, okay? So I'm not advocating for or against. I'm just explaining what they are. Pretty good with that? Okay. Don't go telling anybody your teacher said go get a prenup. That's not what happened here today. Just describing. So when we're looking at the picture of A and B in my universal set. So what really happens in the wedding is that we have this set A and we have this set B. Don't shade it yet because I'm about to erase something. And there isn't anything in the overlap, okay? So if then the marriage were to dissolve, everything that you brought in is the stuff you take out. And then you got to figure out what to do with the stuff in the middle. Okay, so this is the picture of the A with nothing in B. So everything in circle A, but nothing that overlaps with B. So I don't get the intersection at all because I don't get the part that overlaps. Okay. So we're going to take a look at an example of a blended family because a blended family is a really good way of describing this. And so that's the example I've chosen. Consider Mary, single mom to one child, Mark, and Joe, single dad to two children, Jack and Jill. Mary and Joe get married. Together they have two children, right? That's the overlap now, right? The part that they share. Anne and Andy. If M represents Mary's kids and J represents Joe's kids, find and describe the following. So what would the intersection be of M and J? It would be what? It would just be Anne and Andy. So it's the kids they have in common. And from the point we're describing, we're talking biological. I don't mean to say that they aren't all their kids. They are, but I mean biological, okay? So kids in common, biologically speaking. So the kids they have in common, and Hannah, you told me who they were. They are Anne and Andy. Okay, does that make sense? What would the union be? It's all the kids, right? It's the family picture. All right, you get all the kids together to take the family picture. You don't want to leave anybody out. That's what we're looking at here. So now we have the same Anne and Andy as before, of course. But now we also get who? Close. Jack, Jill, and Mark. Joe is the dad. Lots of names, I know. Yeah. Jack, Jill, and Mark. Okay, we get all the kids. What would M minus J be? Okay, so it would be just Mark. It would actually be Mary's, we'll say original children, like the ones that she had before she got married, right? So original kids before she married Joe. So you're right, that would be just Mark. So remember, it's supposed to be all of Mary's kids, which is Mark, Anne, and Andy, the ones that are biologically hers, and then removing the ones that would be also Joe's kids, which would be which would be Anne and Andy. Okay, so that's what that would look like with that kind of a verbal description. There are some properties that that unions and intersections have, and that's actually what we're going to look at next. The commutative property or the commutativity of set intersections and unions says the following. So for all sets A and B, if you do A intersection B, it's the same as B intersection A. And if you think about streets, that makes sense, right? The intersection of Kickapoo and MacArthur is the same as the intersection of MacArthur and Kickapoo. It doesn't matter which one you list first. And it's the same thing for a union, right? The union of my stuff with my husband's stuff is the same thing as the union of my stuff, my husband's stuff with my stuff. It doesn't matter the order you list them in. So commutativity is always about changing orders of things. There's also associativity. So for all sets A, B, and C, if we have A intersect B and intersect C, it's the same thing as grouping the intersection of B and C first and then doing it with A. So the grouping symbols don't matter. And it works for unions as well. The union of A and B and then unioned with C. We could have just as easily done the union of B and C first and then unioned it with A. And the third one, that's actually kind of a descriptive property, really, of these sets, has to do with combining intersections and unions together. So it's the distribution of set intersection over set union. So again, same as before for all sets A, B, and C. If we take the A and do an intersection with B union C, you have the ability to sort of distribute this across. Okay, that's what I'm sort of going to be looking at doing. It looks like distribution. This is A intersect with B, and then union A intersect with C. So instead of doing the union and then the intersection, I could do two separate intersections and then a union, and I'll get the same thing. So there's also these are properties about the actual sets, but we can actually look at the cardinality of the sets for counting arguments as well, and we have a cardinal number formula. So the cardinal number formula, did you guys get it all written down? I apologize. Is everybody good? Okay. The cardinal number formula talks about how many items are in things, and I'm going to draw a picture here to justify this in a moment, but the number of items in the union is the same as the number of items in the sets individually minus the number of items in the intersection. So imagine taking that union picture that we had, well, any of the pictures that we had really to start with, where they overlap, and counting. So I want everything, right, in this whole thing, right? That's what I want for my counting argument for the union. And so what I really want is I want everything in A, so I count all of that up, right? And then I want everything in B, so I count all of that up. And what happened in the middle? I counted it twice. I shaded it in red, so I counted it when I shaded in red, and I counted it when I shaded it in blue. So I shaded it twice. So we have to compensate for the double counting, and that's why we're subtracting at the end. So we're not removing the center entirely, we're just removing it once because I counted it twice. So that's the cardinal number formula and why that works, sort of from a graphical standpoint. All right, there's one more set operation that we're going to look at, and this is the set operation called Cartesian product. So the Cartesian product is the set of all ordered pairs such that the first component comes from the first set and the second component comes from the second set. So I'm going to write them down first, and then I'm going to show you an example so you can see what's happening when we're doing this. So it looks like, it says Cartesian product, so it looks like multiplication with that cross in the middle, right, the X. And what this is, it's the set of all ordered pairs AB such that A is an element of A and B is an element of B. So let me show you an example to explain how it's working. So we're going to let set A be the variable or the letters X, Y, Z. And set B is just going to be our numbers 1 and 2. So if we're finding the Cartesian product A cross B, like actually finding it, we're taking an element of A and pairing it up with an element of B. It's X1. And we're going to do it all with all of the elements. So X can pair with 1, X can pair with 2. Y can pair with 1, Y can pair with 2. Or Z could pair with 1, and Z could pair with 2. And that would be the list of elements. So the elements are ordered pairs themselves. Okay, the elements are ordered pairs. How many ordered pairs did I get? 6. Why did I get 6? Yeah. So there are 3 elements here, and there are 2 elements here. And when you pair 3 elements up with 2 elements, one at a time, it creates 6 different possibilities. That's the fundamental principle of counting at play. That's what it really is. We saw that in an earlier section. So there's actually an additional property. The number of items in the Cartesian product is actually the number of items in set A times the number of items in set B. So be careful what the question asks. If the question asks you to find the Cartesian product, then you're finding all the list of ordered pairs. But if the question simply asks you how many, right, what are the number of items in the Cartesian product, you don't necessarily have to list all the pairs to find that out. You just have to count the items in the individual sets and multiply them. So just beware of what the question is asking. The difference is the N at the front. N means number of. Is there one of those present? If so, then they only need the number. And if there isn't, then they want all of them listed. Okay? Any questions so far? Okay. I want to show you, I think, at least 2 examples. Time for 2 at least. Of some Venn diagrams and how to think about them. So I didn't used to teach Venn diagrams this way, and I had a student come up to me after class, it's been years ago now, and say, hey, Dr. Hands, so I've seen this done before in this way. What do you think? And I was like, oh, I love it. I think it's fabulous. And so I've taught it that way ever since. So this is a very prescriptive way to do it. It's not the only way to do it, but it always gives you the right answer. And I like that. I like the fact that I have a very step-by-step way to always get the right answer. So I'll let you see what you think. So we're going to use a Venn diagram, and we've got 2 sets listed, A and B. So we're going to draw a rectangle with 2 circles inside. Okay? So that's our setup. That's nothing unique. Sometimes we'll have 2 circles, and sometimes we'll have 3. We'll get to the 3 one later. So we have 2 circles. Now, one way to do this one, and it's not too bad because there's just 2 sets, is to reason through it. Well, this says, I want the complement of everything not in A unioned with the complement of everything not in B, and we could probably reason through it, and we would probably be pretty successful most of the time. Okay? But when there become 3, or 3 with complements involved as well, it becomes a lot harder to reason through it. And we're probably not going to be successful, to be honest. Probably not going to work. So this is one of the options for how to work your way through it without having to sort of abstractly piece it all together. We're going to put numbers in each of these regions. There are really 4 different regions on this picture. Spaces. 4 different spaces. And we're just labeling them, okay? And then we're going to look at what we're trying to find, and we're going to identify the numbers that are in those areas. So the first item we're going to look at is A complement. So A complement means everything not in A. So looking at the numbers 1 through 4, what are the numbers that are not in A? 3 and 4. Does everybody see that okay? All right. It also says B complement, so we're going to do that too. B complement, all the numbers that are not in B. 1 and 4. Okay, so far so good. So it's observational, just listing out numbers. The next one is the next step is actually combining them with whatever symbol they're giving us. And they're giving us the symbol that's a union, right? So when I want the union of something, unions and intersections, I'm always either getting everything or the stuff they have in common. It's one of the two. So which one is union? Is it the everything or is it the in commons for union? Everything. Union is everything. Okay, union is marriage, right? Marriage is called a union, right? Marriage is union. Union is everything. You get it all. So I need to write out all these numbers, but I don't need to duplicate it, right? I know 4 is in there twice, but there's no reason to write 4 twice. So I'm going to list all the items, 1, 3, 4. And the reality is I've answered the question, I just haven't done the picture part. The picture part says that I'm going to shade. So I need to go back to the picture and actually shade regions 1, 3, and 4. So region 1, right here, region 3, and then region 4. Something like that. You're welcome to shade with pencil. You're welcome to use highlighters or markers, something like that. I have markers in class when we do group work and tests and things like that. If you want to borrow my markers, that's fine. You guys are mostly elementary ed folk, and you probably carry them with you anyway, so probably not a big deal. But markers are helpful. Any questions on that? Now, honestly, that might be a little overkill. You might have been like, I knew those were the regions I was supposed to shade from the beginning. Why did I put all those numbers in there? Right? That seems like a lot of nonsense for something that I didn't really need that much work for. Well, we're really just building up the work so that we can do things that are more complicated. And in particular, when we have 3 sets, it is more complicated. So we're going to draw a diagram with this one that has 3 circles because it lists A, B, and C. So we're going to do 3 overlapping circles in it, and it starts to look a little bit like, the Olympic rings or something like that when I draw my 3 circles. So there's 2 of them. And there's my 3rd. And they won't get any bigger than 3. So, this is as big as they're going to get. You don't have to label them exactly like I do, but it'd probably be easier in taking your notes if they do mirror mine, so that you have all the pieces in there matching. So I have A and B as my circles on top, and I've got a circle C on bottom, and then there's a U on the outside. It's probably worth noting that your diagrams don't have to look like this in general. For this question, this is what you're going to be drawing, but there are some examples of ones in your homework where they draw a diagram that looks different, like maybe only 2 of the 3 circles overlap, and there's a 3rd circle that's like set aside. Okay, that's fine. It just means you have fewer regions to put numbers in, okay? So it works the same way. This is just the most complicated picture with the most complicated regions, so that's why I'm showing you this one. So what we're going to do is like we did on the one with the 2 circles, we're going to label numbers across the top 1, 2, 3, across the middle 4, 5, 6, in the bottom 7, and then on the outer part of the rectangle 8. Okay, so now we have 8 regions to consider, not just 4. All right, so what we're going to do is we're going to do just like we did on the other one. I meant to move C though. Okay, so this time we need to actually pay attention to where we're starting. I have parentheses, so I need to start inside the parentheses. The parentheses say A intersect B. Now you might be able to jump to that part of it, but we're just going to do it again piece by piece because sometimes it's not always A intersect B. What if it's A complement intersect C or something, right? Like it's messier sometimes, so we're going to be really careful and we're going to write out A and B individually. So what numbers are inside set A? 1, 2, 4, and 5. What numbers are inside circle B?
2, 3, 5, 6.
And it says I want the intersection of A and B. What does intersection mean?
Which are the same in each one?
Yeah, the common ones, the ones they have in common or they share. What do they share?
2 and 5.
Okay, now look back at the picture. Does that make sense? Thinking about overlaps over here, right? The intersection being the number 2 in this diagram. Is the intersect of A and B 2 and 5 right here? Yeah. So it's conceivable that you could just start at this spot and just not do these pieces. And that would be fine. On this particular one, that would be a perfectly reasonable thing to start with and then continue from there. So again, we're working under the premise that they're not always that easy, and they aren't. So the next set that it describes is actually, oops, sorry about that, set C out here. So we're going to list the items now that are in set C. So what numbers are in set C?
4, 5, 6, 7.
Thank you, Faith. 4, 5, 6, 7. Okay, so I've got A intersect B, that's one of the sets. And I've got C, that's the other set, and they're listed here. And how does it say we're going to combine them? A union. And what does union mean? You get everything. So I tend to write things in sort of increasing order, so without repeating. So I do 2, 4, 5, 6, 7. Those would be the individual components. And I would go back and shade them. I have circled part 2, 4, 5, 6, and 7. And this would be the shaded region corresponding to that image. Any questions on that? Okay, we have enough time to start the next one, but I don't think we have enough time to finish it. So I'm going to push pause right here, and we'll pick up with example C next time.